So thanks a lot. And thanks a lot for the kind invitation. And kindness is a bit of a double-edged sword, okay? Because on the one hand, yeah, I'm very glad to be here. But on the other hand, yeah, I come as a bit of an ambassador of somehow the mathematicians who are not here. Okay, so let me put the things straight here. So yeah, I'm a geometer, okay, and I got interested into these topics. So what I've done essentially is here I've supervised at UAB some final year projects on these topics. And now, very recently, I'm actually finishing. I got myself to teach a course on both the mathematics of machine learning from a pure mathematician viewpoint, but also these applications of mathematics to machine learning, which I'm not going to talk about today. So this is going to be quite naive and biased overview. Okay, sometimes it will be very basic. I apologize for that, and it may also feel quite uneven. Uh, so let me start by opening this book on statistical learning, which is kind of a established reference. Okay, if I open this book, I see first chapter. I see that they are worried about some budgets of advertising on TV, on newspapers, on radio, and they have an output, which are the sales. So let me leave this book open here on the table, and let me now go back to the year 2000, beginning of the uh, century. We okay, wrong. So I since that not do with the statistics, let me do some very simple statistics now. I would like you to raise your hand if you were born before 2000. Okay. Okay. And now, who of you remember that 2000 was the World Mathematical Year? Okay. So look, when I was preparing this talk, I thought it was a great event, like something very big. But now you go on the internet, okay? It's time ago. I know for the very young people, it's like, come on, it's 25 years ago. Yeah, but still, Google started in 1998. There were like search engines. You go on the internet, and all you find are four stumps, okay, of that thing. There is only one Wikipedia page in German, okay? And at that point, the year 2000, to study math, I guess everywhere, in Spain at least, he just needs to pass the exams, okay? It was 5 out of 10. Now, this is not like, okay, 25 years ago, okay, let's see what happens since then. So that's the curve of like, this is the average grade, and this is the grade you need to enter, okay? This numerus clausus thing. And you can see how it went up. Of course, that one maybe, if they're not from Spain, may think, come on, you are going until 12. This is not okay. The system in Spain at some point they decided to do it over 14. Okay, don't ask me why. And you may think, okay, that happened in 2015 for sure. No, it actually happened in 2010. So still these years over 14. Okay, this was what you need to study math. Now, many people who studied math, including myself, in these years, we were kind of really passionate, and the people I met about math, something very pure. Okay, and I didn't care. I wasn't interested. Okay, there are two issues here. One of them, this is quite slow. The other one, I feel wind when I talk. I don't know if you have something. No. Okay. Okay. And now this is stopping. So now no interest in predicting cell. I was going to say also no interest in machine learning until 2021, when there was this paper on Nature that was somehow showing how AI was used to guide mathematical intuition. I wasn't interested in that, but I saw one of the authors was Jordi Williamson, and I met him personally. I actually worked for him as a teaching assistant at Tabion. And then I saw he was organizing some seminar in Sydney about the topic. I went there and I had him also as a pure mathematician telling about machine learning. And this is how I got interested in this topic. Okay, so then I realized there was this perspective that wasn't quite the one in that book. Okay, that is very appealing as well for mathematicians, and somehow this is what this talk is about. Now, in the book, okay, we had this budget, and the output were the sales, and the idea what they want to do is under this distribution. Sometimes they say, okay, in the products, sometimes it's just y given x. Okay, this to a mathematician like me, I mean, in the last, I mean, not now, but in the previously, okay, from 2000 to 2021, it's better if you just tell me you don't want to learn a distribution, okay? Let's say you have some samples of a function, and we've seen this around also yesterday. Okay, we want to learn this function. That's all you want to learn. Of course, a mathematician first he would say, okay, come on this, I just want to interpolate the samples, right? Say, okay, not quite. Forget it, because we're going to start using neural networks. Let's say these two sets you have, for example, this leads in our end, so that we have some fields, okay? And we are going to learn a function like this. Let the mathematician say, okay, but what is this thing of neural networks you are talking about? Okay, so what is a neural network? Now you go to book neural networks of is 94 is and this definition is given quite philosophically, okay? Okay, maybe good for your neighbors, not for a mathematician. Okay. Now, many times you also say, okay, this is the thing. Okay, all these notes, all these lines, everything here, there are weights, there are biases, there are original layers. Yes, okay, this starts to feel nicer, but still I think if a mathematician asks better, very young mathematician asks, what is a neural network? You should just tell it's an so an alternate composition of affine functions and a navigation function that you are going as its reducer. Okay. Here's the first definition. Okay, I know there are different types of neural networks. This is vanilla one, the secret one. Okay, so this is, I think, how we should start. And this is a class of functions. And once you fix sigma, this activation function, it will depend on some parameters, which are essentially these are five functions, a matrix and a vector, so you can count how many parameters you need. Okay. Now, what is the sigma? Just for completeness, this is the topic of this talk here. So it's a function like this. Like, of course, we said Lee has always do the bash, but this is how somehow they started looking at functions like this, and now it turns out that the most acceptable one is this real thing, and it's an interesting thing actually because I mean how this thing that is simpler gets better results. I like one of the explanations I like that I heard is that actually this linear, as we will see, does not. Okay, but ReLU is not linear, of course, but it's actually linear for multiplication by scalars. Okay, so for the two properties of linearity, you still keep one, and that actually gives you some advantage later. Anyway, you gave this mathematician this class of functions, which are these neural networks. And now the question is, okay, you wanted to approximate a function. How well can you do with these networks? Okay, so now I'm going to say to fix continuous functions on a compact set of Rn. I'm going to consider the infinity norm. Okay? So the infinity norm is when we want to approximate a function, what I want to do is to say, okay, we put an epsilon and we'll do like a band around that function, and I want the approximation to fit that band. Okay, the uniform. Okay, and now what I'm going to do is in each of these cases, I will specify what is this activation function, the relevant sigma thing. So it turns out that from all this composition of affine function with the sigmas and everything, having what's called p layers or only one hidden layer is enough. Okay, and that's a progressing result. It was already observed in 83 for sigma continuous and what's called sigmoidal. Okay, that limit there 0, limit there 1, and here whatever happens. Now, people started to work on different hypotheses for sigma, and in 91 was a result that actually you only get them continuous, bounded, and non-constant function approximation. Okay, there were many other works. I wanted to highlight these two, but especially the third one, because there was this question of whether you could approximate well with a function that is not even continuous. And then in 1983, there was this Legers and theorem that it tells you two things. That first of all, that you can actually approximate with function that has a null set of discontinuities. So they actually were playing with this discontinuity aspect, but also they establish like an equivalence, okay, within this framework of when this class of functions, these neural networks, actually are dense. Okay, and this is an even only result. So that is very nice. The other result were take this sigma like this, you approximate. And this guy said, okay, within this whole box of sigmas, which is a very big box, you will approximate if and only if your activation function is non-polynomial. Okay, so a mathematician may think about polynomials actually approximate part one, right? Because you study Weierstrass theorem, and you can say, okay, but you know that polynomials are able to approximate everything. Okay, but of course, when you allow for any degree, okay, if you fix a degree of sigma of this polynomial, then you apply only one hidden layer, the only functions you will get in this class of neural networks will be just polynomials up to that fixed degree. Okay. Now, it's interesting to involve this Weierstrass theorem because actually, somehow this number n1 works a bit like the degree of these neural networks here. Okay, so you cannot, if you fix n1, you're not going to approximate any function. Okay, but actually, when you allow n1 to go as big as you need, then you can approximate any function. Okay, in the same way that happens with Weierstrass and the degree of the polynomials. Just quick remarks. The proof I find it's very beautiful how it combines this convolution and like a distribution theory. It's very nice to read. Okay, could be organized a bit better, but it's I found it like I really enjoyed it. Okay, like devoting the time to understand how it will get. There are also results for other function spaces, actually like tailor spaces for very finite measure. And this thing I say here is that it's surprising how in the literature, if you see the citations of this work, and this work, sometimes somehow the number of citations times the generality of the result is constant. Okay, the minute that this guy has 22,000, it has 14,000, and these guys have I think like 3,000-4,000 citations. Okay, so we just recommend that result. Now, if you say one layer is enough, so you can ask the mathematician, okay, why do people grab all this deep learning? I think you need to go very far, and if one layer is enough, okay. And actually, in 1999, here I hold a comment for the local people. In this paper, actually, you can see how Alas Vincus sites are also like again. It wasn't clear. Okay, you could see people were starting to understand that that this thing of construing more layers would give you some advantage. But it wasn't clear at all. Okay? Now, I'm just going to mention, without entering into details, a result I find also interesting from a mathematical viewpoint is from Daniel in 2017. Somehow it's going in a very precise way mathematically and actually using like big math is that like with more layers somehow it will leak fewer errors. Okay, so that when you do it with one layer, you can approximate everything, but perhaps your growth will be like you will need an exponential number of viewers to approximate, and then if you go to something more layers, then you can use somehow for some family some accuracy a polynomial growth. Okay, that's an idea that I brought there. What it interesting is actually that it wasn't until 2020 that someone established in this generality, because the world works before, an approximation theory in the same way of calculation using English and show for the networks that were not like this single layer with this n1 being very large, but what's called deep narrow, to say no, I'm going to allow for many layers, But what I want to do is to restrict the width, okay, which is the dimension of that space that I'm putting in the middle. So it's quite interesting how they tell you if you want to go from Rn to Rm, okay, so you can actually fix the width of your layers, hidden layers to their sum plus 2. And now sigma, this thing of the polynomial was essentially for one layer, okay? When you go for more layers, you can have polynomials there. And actually you can see the condition they give is quite weak, okay? Or what the function has to be, okay? Not applying with just at least one point is not your derivative, okay? It's a super weak condition in this result. Okay. So now we know that they approximate very well either one layer, many layers, they do that more efficiently. And the question is, okay, but how are you going to approximate? Okay. So let's start with approximating at a given point. So let me review this. Now, the function we want to approximate depends, like our approximation will depend on the choice of some weights of these are the people choose the parameter space. So can I put this number like explicitly before? And this function is going from Rn to Rn. So the idea is instead of doing that, since I fix the point x, I want to see the function as something going from the space of parameters, this w, to Rn. Okay. And now I have the function like fx instead of fw. And now we want to compare this thing for an even choice of weights, polarities from the actual sample, okay? Because that's some of the value of the function I'm trying to approximate. And for that, you can take some function just to measure the distance or semi-distance I put here to that point y. Okay, why do I say semi-distance when I going through this material and then one to naturally as a mathematician put the distance, okay, and then you see that everyone is using the mean squared error. Okay, the mean squared error is not a distance. Okay, it's the square of a distance. So it doesn't satisfy the triangle inequality. But that's okay, okay? Because so it's the same distance. And actually, in terms of the topology that it generates, because you're just taking a power of a distance, so it is the same. Okay, so you are very safe. And once you know how to measure the distance of your prediction to y, so the example, what you want to do is to minimize, to adjust the ways to minimize this loss here, okay? And this is how the whole story of the gradient descent enters. So let me review that. So now you want to minimize that, and you say, okay, so what I'm going to do is to see the direction in which this function, the direction in which I have, like infinitesimally, I like descending more and just move around that. Okay. There are many subtleties here. One of them is that if you put this feature of a function like this, you say, okay, chances are this is not going to take you anywhere, but still then it works. And somehow, even though I don't understand that fully mathematically, but the ideas I like that are behind is first of all, in one variable function, you can see there are very local minima. So as you grow the dimension, it's very unlikely that you are going to have as minima because you're going to have many directions. So the likely critical points of your function, they are going to be saddle points. Okay. Like these saddle points actually we also saw in this how you move from saddle to saddle. Okay. So they something like that's something that will help us for this optimization, and also like the symmetries that the theory may have based on the value of the linear and also symmetries of the in the space of parameters because I can't forget. In any case, I wanted just to make a comment about this thing here, because when you compute the gradient of this loss function, one of the things you have to do is to compute this Jacobian, okay? And computing this Jacobian is what's called the famous backpropagation, okay? And then many people, I don't expect to read this, many people say backpropagation is a chain rule, which I agree on that, but kind of when you go to the Wikipedia, and I represent Wikipedia as great for many things. I don't like the entry for backpropagation of Wikipedia. Okay. It goes first, it does some simplification, okay, amount for simplification, as you would see. But still, yeah, it starts to put a very long expression here, and I don't okay, it's matching logically, okay, but why why is this such a? I mean, here's how this change. Well, why these people just rebranded it and started to sell it as something very nice. Okay, so and the thing to understand it better, I feel it better just to look at a very simple example. Okay, so here I'm just adding all those are real numbers. So this is just going. So you have six parameters, okay, that are real, and you have a function that goes from R to R. Okay, now this is the function easy to understand as a function that goes from X to Y if you fix A, B, P, Q, R, and S. But now what I want to see is to fix X and see this as a function of A, B, P, Q, R, S. Okay? And now I have the function I can compute. What I want to do is this gradient is the derivative in the directions of the parameters. And this I did import, and these are the things. Now, what you notice here is that actually some bars are repeating. Okay? So you can see some things appearing twice. For instance, here this term R sigma phi, this whole thing is going to actually be appearing also here. So like exactly this term here is this term here. So what I can do is to, instead of saying you have to compute this again, you just take this derivative. Okay, and this is what it becomes. Okay, now I compute this and I will come here. And once you got this and you got these bigger biases, okay, with the bias selling, which are the like the independent variables of the five functions, you can see that in blue you have the way you are to compute the image of a point x. Then you do ax plus b and you apply then you apply sigma, and then you do p sigma x plus b plus q, and then you apply Shiver. Yeah, here you apply spread. So all these steps in blue are things that you get when you apply just the function you have placed. And the other ones are just you start here, you plug this one here and here. Okay. Once you have this one, this you will use here and there. Okay. And this is the way this is actually simplified, because if you see, we only need to compute the x, gives few things here, which are the steps of its image, and start with this one. Okay. So backpropagation works out so well because it's a composition and you apply the chain rule, but you have to see what function you apply the chain rule to. That this is something I somehow don't see so often when I know, but I haven't seen it, so I did it myself, which is actually you have a function of the parameters, and the whole thing of batch propagation is that in many of these compositions, like the parameter will stay the same. Okay. So just start with many parameters, and what you do is with the x, which is given fixed number, you have this function, which is very simple. You apply the sigma, then you will do the same, just this small thing, and the rest will be the identity. So this actually takes that when you want to compute then the partial derivatives of this thing with respect to these things here. So once you hit one of these, it does go automatically, okay? And then you have this recurrence relation, which is also by the way these functions are, which are very simple. It's just the alpha and sigma, okay? So I agree that propagation is a chain rule, but of the right function. On the other hand, this is just a one variable example. What happens when you go to matrices? So when you go to matrices, you take one good reference on the subject, which is this one here, the Sunny Machine Learning, you can see how you at some point, okay, we said the function goes from R big D, which is the number of parameters, to R end. So if I want to compute the Jacobian, that's an n times big field matrix, okay? But in order to do that, you have to start together all these coefficients, all your weights, and here there's a sentence, a vector of them by concatenating the rows of these other weights. Okay, you will get a massive vector. So this thing you can make it work. I find it also very confusing, and somehow working against our target of understanding things better. And what I think we should do is just take what we have, which is just this backpropagation in one variable function, and if now you go for matrices, you will get this. Okay, so here, okay, the only thing that has changed apart from the capital letters is that I will have here some diagonal thing that I repeat in the test. Now, what are these things? These are not dangerous anymore. Okay, these things here, when I put the Jacobian of R, the Jacobian of P with respect to the matrix R is a matrix, okay, and I'm not stuck in that matrix. I'm considering as a matrix. So what I'm doing is the F has different components. What you have to do is the same you do with the Jacobian, that you say, okay, I know how to compute the gradients. So I will do the Jacobian, but put in the gradients, okay, in the row. So now you have to do is, okay, if now you have, instead of a vector of variables, you have a matrix of variables, in each of these variables, you have to put the gradient, okay? So what you end up with is with a three-dimensional thing, okay? Three-dimensional basis. And this is something very natural, I think. Okay, the thing is that, okay, foods, many times we didn't use it because no one told, okay, learned how to use these higher dimensional matrices, but these are called in this, and I think we can assume these tensors, okay? These are these arrangements that can have as many dimensions as you wish. And actually, yeah, the products, everything will work very nicely. And actually, this is the reason why also this algorithm is so effective, okay? Because all these operations are optimized for those tensors, okay? And that made it so successful. So actually, I think we should embrace these tensors, and because they are mathematically sound, okay? Is what's really happening here. And the second reason is because there are many works on matrix multiplication algorithms, and the way you formalize a matrix multiplication algorithm is via tensors as well. Okay, so it gives you access to all these very recent, very interesting works. Okay, so now we for a point. Okay, so we got to the mathematician. Okay, yeah, you do this like for measure points, and you will make sure your function will adjust to all these points nicely, and then the mathematician may joke, but we're only matching the substance. Okay, and not even that, we're not even interpolating, at least you know you get the right value. But now you're just approximating the value for Sandler's modeling. Okay. So then here there is this trick, okay, which is very well known. She's okay, you take 80% of your sample and you learn by that, and then you test on the rest 20% or other percentage you want. And this way you at least, okay, they know that if it doesn't work like that, it's because perhaps there is no function behind your sample, okay? If it works, there may be a function or there may be not, okay? Now, even assuming there is a function, or you say, look, you had here some data, and now I can relate your inputs with the outputs, the mathematician may feel, okay, but you are giving me a massive function, and I don't have any way of eliciting some information from it because it's just like millions of weights here. Okay. And that's why the attribution, this is okay, the attribution can. Okay, so the idea is that if we see how these n as features of our data, and we want to see what is the relevance in understanding the output, okay, if this was a linear function, this will be just coefficients of these n variables here. Okay, but this is massive amount of data. So there are some works that actually surprise me that they are kind of quite having in mind that all the like somehow perceptions, neural networks started around the middle of the 20th century. Okay, so only like the to say just to say one way of doing it is by gradient and applying this. So Benedict signed this paper from 2013 just by saying, okay, you know how it depends here. Basically, take the partial derivatives and to see somehow what's the variation. Okay, that of course has some issues, especially when you deal with samples and with noise. And then there were two methods, like 2016, 2017, and very curious that they came exactly from the same university, from University of Washington. And one of them, this has a very nice idea, which is you want to approximate a point. So take points around it and try to, for that point, or what happens in that point, try to approximate with something you can understand. And that something is usually some linear thing. And then you look at the coefficients. And the one that somehow became more successful, and here you can see the uses of sharp and of line through time. the repositories in GitHub, is these Shapley values. Okay, so these Shapley values, they brought me to a interesting piece of math as well, which is comparative game theory. Okay, so these people were interested in the yeah, say in these ones in particular in the peak around the 50s. So what's a comparative game? So you have players, and now for every subset of players, you give what's called the worth. Okay, this think about the money you will get if you play together. Okay, the idea is that you play all of you together. Okay, and then what you want to do to solve is how, if you play all of you together, how are you going to distribute this worth? Okay, so this is the question that is posed here. Now, the how do that? So the person who established this theory wanted actually to do it for all the set of all games. Okay, we say okay, every game will have one of these value functions. Okay, these are PDEs for every player. If I'm going to get a real number, and if you want, first of all, that if you play a game, okay, and you get a certain amount of, let's say, money to it, you are going to distribute all the value, right? All way to keep money apart. So this is the push. The second one is saying us that if you are playing a game, okay, and there are two players, and whenever we put one or the other, the worth, okay, you will get with this function, okay, is the same. So when you distribute the total, these two players should get the same. Right? That's called synergy. Now, if whenever you put someone with any combination possible, that person doesn't change at all the worth, so that person should get nothing. Okay, the null player. And then he puts this condition, which is additivity. Okay, which is now you consider the sum of two games and you want the value of the sum of two games to be the sum of the values. Okay, this I have to say from a mathematical viewpoint, okay, that's great. Okay, yeah, it has a different flavor. Okay, but the Hebrew there is only one such function, and this function is actually sharply valued, and there is usually is a formula with many factorials there, which is equivalent to this one here, which is already explained in the original paper, and it's basically just considering all the orders of the players. Imagine you have a line of players and say, okay, the first player, if it plays on its own, we will get this money. Now, the second player chance. What happens if the first and the second play together? There is a difference in how much they gain. Okay, so you start to, for every order, okay, and say for each player, how much it contributes to the difference of work. Right? You are going to take as an average of this. Okay, so this is just the average of the contribution of this player to any order you give to the players. Okay, so here there is the thing is okay. How can you use that all this whole uh, game theory to to know what's happening in the approximation of a function? So you play a game for each point, and the game for each point is given a number of variables of entries of coordinates of your point x. Okay, you're going to fix those in your function header. So you are going to, if x say is 1, 2, 3, and s is I'm going to say that x is 4, 5, 6, and s are the coordinates 1 and 2. So then you are going to compute the expected value of fixing the first and the second coordinate to the values of x, to 4 and 5. So you would give as the worth of these coordinates this expected value, and there is a very nice idea that how can you see every feature, every coordinate of this space of parameters, how it's contributing to arrive to the final value f of x. So first you start with the mean of all the values, say, then what happens if you fix the first coordinate? So the mean goes, you can see how the mean goes, and then you're right here to the band, okay? You do this in all possible orders, and then you get this in here. The thing is that this is actually just a game, of a point. Okay, so before, in order to get a unique Shapley value of this, you have this additivity condition, which feels a bit foreign. So additivity can actually be replaced, but still for with a condition which is called strong monotonicity that involves two different uh, gains. Okay, and I found very surprising, but also very recently, that actually there is a way of also an axiomatic way to sort of determining this value uniquely with what's called the gain potential, which was developed by Hart and Muscular. And this also, like, it's kind of an axiomatic definition that is enough to consider a gain and all the possible subgains. And this is now a method that can be used to interpret that is used to interpret these approximations. Now, the mathematician may say, okay, now it's been a long time with this single supervised, but actually what I see around is that people are not using so much supervised learning when they are doing all these things of the matrix multiplication, and even now with Lee and also, like, if they're using reinforcement learning. So now, what is this reinforcement learning? So as a mathematician, you just need to do set of states, set S of states, set A of actions, and this probability distribution that on each state and each action, it will tell you, if you take that action as that state, what is the probability of landing on a new state, and what is the reward as a real number that you are going to get. And the problem you want to solve is you want to find the probability distributions on the actions for each state such that if you flow with it, which is you start with S, you take some action probabilistically, okay, you will get some reward probabilistically a lot, and then you land in a different state where you will choose a new action and you will keep on getting rewards and states, rewards and states. So now you take all the rewards, you multiply by some what's called a discount rate for this to converge when you have bounded rewards. And this is what you want to maximize, and you want to find this policy. Okay, this is reinforcement learning. Now, there is a theory behind this, and the theory is that essentially, if you assume these two sets to be finite, you can, okay, here there is missing a line. Okay, you can, for each state, say what is the expected value of this thing when you follow the policy phi when you start in the state S. Okay, this is the value of a state for a policy pi, and you want to find a pi, optimal pi, which is the value of a policy of the optimal policy will be higher than the value of any other policy, and this in any state. Okay. Now we go to this book, which is like establishing this theory, and what you find is that they claim there exists such an optimal policy. Okay. They say the same, but they don't actually go very like, okay, they're going to say, you're going to prove this. Okay, actually, if you look for the word theory, you see that essentially there are two theorems in the whole book. Okay, it's very influential, very important, but for a mathematician, it's not worth it. Say I'm going to read now 524 pages of things. Okay, so now what actually happens is that these values are related to each other, and it's very easy to deduce. I knew at this time I have very little time, so I didn't put the deduction, but it's a two-line deduction to get this equation about with of the values of a given policy on all the states. And this is a linear equation. And this linear equation, Jan just solved it and compute the values of a policy. And here the idea is that if the optimal policy exists, it turns out it has to satisfy this other equation, which looks very similar, but instead of taking a mere probability, you are saying just the sum over the A and the probability, you say just take the maximum. Okay? And as a mathematician, okay, this is something nicer, because then you can see that some people care about saying, okay, if the optimal policy exists, satisfies this, now we see that we have here the same the value of the same policy, this optimal policy, different states. So actually, this you can see it as an operator. So for any function on the states of this setting, you can define this operator, and this operator is acting on the function space, functions from S to R, and you can see that if you give this a reasonable metric, this is a contraction. And with that reasonable metric, it's also a complete metric space. So if you have a complete metric space and you have a contraction, what you can apply is balanced fixed point theorem, which tells you that there is a fixed point. At that point, fixed point is zero. And actually, it can be found to by iterations. Okay. And actually that has practical implications for the for some algorithm. Okay. Now, the thing is also this to start with, this optimal policy is going to be deterministic. Okay, that run like here I put all this phi and everything. At the end of the day, it's going to be deterministic. But the thing is that it's very nice how considering this phi will allow the algorithms to find it. Now, to stitch the two bars, okay, the supervised and this reinforcement thing I said. At the end of the day, one of these policies, this pi of h given s, it is just for a given x, I have to give a probability distribution on the possible tails. Okay? So now, if you as a mathematician say, oh yeah, that's the thing, then now you tell the mathematician, come on, I told you at the beginning, it was better to use the probability viewpoints, okay, to deal with these things. And we did the function one because it tells view. And the thing is that as a mathematician, you say, okay, but now that I know how I can do supervised learning approximate functions, now what I can do is, sorry, this is probability distributions on this finite set, okay, I can see them as a Euclidean space, okay? And to do that is then, okay, we've seen many times with softmax function. Okay, the softmax, the only thing is do it, okay, this case is it does allow me to see a probability distribution on m elements as an element of R to the m. Okay, almost here I say almost because of course here I don't have zeros, I don't have ones when I do this. Okay, of course R to the m is something open and it is something continuous. But as long as I'm happy with that, I just see these probability distributions as some R to the n. Okay, so actually now if S, I also can put it as some R to the n, I will be in the setup of the beginning. In this supervised learning theory, this just I'm learning a function from some Rn to some Rn. Now, what is the key difference between this supervised learning and this reinforcement learning through this viewpoint is actually when you do supervised, the samples are given to you at the beginning and that's it. Okay, these are the ones you have to fill. When you do it through reinforcement learning, what was happening because you do this thing of playing the game many times, you are generating samples as you play the game. So you generate samples, you adjust, and then you play the game. And then what you do, okay, do this thing of taking the games that will have the highest reward and see on each state what action did you take. And those things you take as samples that you want this function to learn. Okay. So something that I found that it's kind for me, it's the main difference, okay, is the way you get the samples, not so much what you are going to do, which is actually approximate also this function via a neural network. So now the partition may tell you, yeah, that's very nice. You're going to use cross entropy here. This is my last technical slide. It's not very technical, you see, I think going down, which is how do you explain now to a mathematician like me what cross entropy is, okay? Cross entropy, I need to know more about that, okay? And now it has very nice name, but if you want to explain something like the first time, you just have to say, okay, look, you wanted to approximate distribution, right? So let's say you want to approximate 1 and 0, and you do it by p and 1 minus 3. And then you can go give this distance, which is if I take this means for error, it will be this function here. And now the practitioner tells you, yeah, in these situations, you try to use cross entropy. Cross entropy is just take the value here, well, with a minus, everything okay, but this value times the logarithm, this value times the logarithm of this, okay? It's just this in here, in this case, okay? You do this. and you get with the minus, we put the minus and get something positive. So minus 1 times log, minus 0 times log, and you get minus log Q. Okay. Now, what you are really doing, okay, is just punishing this configuring of predictions. Okay, here, of course, I didn't put the 0 because this goes pretty clear, okay? But this is just what you want. This the mean square error is very mildly punishing like these wrong predictions going here to 0. Okay, so you want to have instead minus log x. Minus log x, you will start here like this, and then we'll go to infinity. Okay, so that's actually the first here I put very far from cross entropy 101, okay? But that's the basic idea. So I actually think these simplifications of the models is what's going to allow to work together on these things. And I see somehow this mathematical understanding as the bridge to join forces on understanding what's going to be this topic. And then they just finish by saying, like, in this line, one of the key things we do here at the Bar of Mathematics is colloquium that we do only 3 times a year. And we try to bring, mainly we try to bring like high profile mathematicians, like Charles Fefferman Philpella, who later, or actually he got interested twice in his career about pigs, to tell us about their perspective. And this year, actually, we have also a person from computer science. If you know what RSA, the cryptography method is, so he is the S of RSA. Okay? It's a person who has very nice insights about, this interaction of mathematics and machine learning. And yeah, we hope to learn more from there. And I thank you all for your attention back then.